We're now going to talk about several laws that when we combine them make one overarching ideal gas law. The first law that we're going to look at is Boyles Law. And Boyles Law relates the pressure to the volume. Remember that pressure is caused by molecules striking the sides of the container. So if we decrease the volume, there's going to be less distance for the molecules to travel before they hit the container. So by decreasing the volume, we increase the pressure. And the opposite is also true. If we increase the volume, we decrease the pressure. If we want to think about an application for this, if you are scuba diving, every 10 meters of water relates to about 1 atmosphere of pressure. So as you dive down about 20 meters and you come up to the surface quickly, your pressure is going from 3 atmospheres at 20 meters to about 1 atmosphere at the surface. So if we think about Boyles Law, what is going to happen to the breath in your lungs if you're holding your breath? Well, it's going to expand by 3 times. If the breath in your lungs expands by 3 times, this is going to cause damage to your lungs. So this is why it's important when you're scuba diving to always exhale to release that pressure as you're coming to the surface. The next law we're going to look at is Charles' Law. And Charles' Law relates the volume to the temperature. Charles was plotting the volume of many different types of gases, and he noticed that if you extrapolate the data colder, there becomes one point that all the gases intersect at. And they intersect, at that intersection, the volume would be 0. And this happens at negative 273.15 Celsius, or 0 Kelvin. And this is absolute zero, where all motion ceases and we would have 0 volume for our gases. I know it's been a little while, but did you hear about the guy who froze himself to absolute 0? He's okay now? He's 0 okay now? Okay. Avogadro's law relates, as you would guess, moles to the volume. So the volume is directly proportional to the amount of gas molecules that are present. As you have experienced this with blowing up balloons. So if you blow up a balloon, as you're increasing the amount of gas particles in that balloon, that volume increases. The way that we count these numbers, or the number of molecules, is in moles. The interesting part is that equal volumes of the gas contain the equal number of molecules. It doesn't matter which gas we're talking about. If we have an equal volume, it's the same number of gas particles if everything else is held constant. When we combine these 3 laws together, we get the ideal gas law. The ideal gas law, we have a proportionality constant called the gas constant. We represent this by R. R, when we're using units of pressure and volume, will always be 0.08206, and the units, you'll notice, are atmospheres times liters divided by moles times Kelvin. And the reason for this, for these interesting units, is to make sure that all of the units in the problem cancel out except for what you're trying to find. But this does mean that the pressure needs to be in atmospheres, the volume needs to be in liters, and our temperature has to be given in Kelvin. If we hold other variables constant, we can find all the other gas laws that we've already talked about. And it also allows us to find one variable if we know the other three. Now P stands for pressure. And again, that's going to be units of atmospheres. V is volume in units of liters. N is the number of moles. R is the constant, 0.08206. And we have atmosphere liters per mole Kelvin. And T is the temperature, and that is in units of Kelvin. So our ideal gas equation is PV equals nRT. So let's look at an example. How many moles of gas are in a basketball if we've got a total pressure of 24.3 psi, a volume of 3.4 liters, and a temperature of 25 degrees Celsius? Well, if we look at our units, we can see that we are going to have to do some conversions. What units need to be converted? Well, our pressure is in psi, and so we are going to have to convert the psi into atmospheres. And when we do that conversion, we get 1.6531 atmospheres. Our liters, that is all right. Okay, so volume wants to be in liters, but our temperature is going to need to be converted. And so for temperature in Kelvin is the degrees Celsius plus 273.15. So if we put 25 degrees Celsius into our equation, we see that our temperature is 298.15 Kelvin. We're going to use the ideal gas equation, and we want to rearrange it to solve for moles. So our number of moles is going to be PV divided by RT. We had to move the RT to the other side. Now we can substitute in the values that we found. So the pressure in atmospheres times the volume in liters divided by R, which is our ideal gas constant, units of atmosphere liters over moles Kelvin, times our temperature in Kelvin. Now if we look at our units, our atmospheres cancel, the liters cancel, the Kelvin cancels, and we are left with the number of moles. So in our basketball, we have 0.219 moles of gas. Here's a problem for you to try to find the volume of the gas. Please pause the video and try to calculate the volume. If we look at the variables that were given, we see that we've got a pressure. We know that from the units, so we want to convert our pressure into atmospheres. This is an important conversion to remember. 760 millimeters of mercury is 1 atmosphere. So this gives us 80 atmospheres. We also need to convert our temperature. So we want to take our degrees Celsius, in this case -23 degrees Celsius, and add 273.15. So we end up with 250 Kelvin. We have one more piece of information, and that is the 637 grams of sulfur dioxide. 637 grams, because we know it's sulfur dioxide, we can use the molar mass to convert to moles. So if we add up the sulfur plus 2 oxygen, it's 64.07 grams for 1 mole the sulfur dioxide. This gives us 9.942 moles SO2. Now we want to use our ideal gas equation, PV equals nRT. We're going to solve for volume, divide both sides by the pressure, and we can substitute in our amounts. So the number of moles that we just calculated times the ideal gas constant, 0.08206, times our temperature in Kelvin, 250. All of this is divided by the pressure of 80 atmospheres. So if we solve this, we see that the volume is equal to 2.55 liters of SO2.